This is a video on section 7.3, qualitative changes in equilibrium systems. We'll start by defining Le Chatelier's principle. Le Chatelier's principle states that if a closed system at equilibrium is subjected to a change, processes occur that tend to reverse that change. So when you have a closed system at equilibrium and there is some external change to that system, processes will occur to reverse the change that was placed on that system. In this next section, there is a demo that should be performed in class to help you see the effect of imposing a change on an equilibrium system and how that equilibrium system responds. Just to highlight for you, however, this symbol right here may be a new symbol that you haven't seen yet, and that is basically an equilibrium arrow. So that's an equilibrium arrow, indicating that both the forward and reverse reaction are taking place at equal rates. So before we can move on to discuss further concepts in equilibrium, we have to learn certain equilibrium language. So when we talk about a system shifting left or system shifting right, there's a certain side that is favored. So, for example, if you have a reaction that is L, okay, for left side of the reaction, equilibrium arrow, going to R, which is the right side of the reaction. When the system shifts right, the products are favored because the products are on the right side of the reaction. The reason for that is the forward reaction temporarily speeds up more than the reverse reaction, and the mixture will have a greater proportion of product than there was previously. If a system shifts left, however, that means that reactants are favored. Okay, so system shifting left means it's the reverse reaction is speeding up, right? So you have more reactants produced. So we would say that the reverse reaction temporarily speeds up more than the forward reaction, and the mixture will have a greater proportion of reactants than previously. When we talk about a system shifting as a result of a stress imposed on the system or a change imposed on a system, the changes or types of stresses are listed below here. So one thing that you can do is you can change the concentration of one substance. So for example, if you increase the concentration of one substance, then the system will shift to consume or reduce the concentration of that substance. So the system will shift to consume that substance. So this makes sense because you are increasing the concentration, that is your stress that you're imposing, and the system reverses that stress by reducing the concentration of the substance that has just been increased in concentration. Okay. If you add heat, the system will shift to remove that excess heat. If the volume of a reaction chamber is decreased to increase gas pressure, then again the reversal of that is that the system will shift to the side with fewer gas moles So fewer gas particles to lower the gas pressure. So if you increase the gas pressure by decreasing volume, then the system will shift to the side with fewer moles of gas to lower the pressure. You can also increase the pressure by the addition of an inert gas. And what happens here is that this results by adding more gas particles, okay? However, gas particles that are not reacting with anything, there are definitely more collisions. So there will be more collisions. However, there will be no change to the system. So that is to say, no shift, or NS, because the addition of an inert gas has no effect on the system, right? There are more collisions, and potentially you may have the reaction speeding up, but the reaction will speed up in both directions. And the same thing is to be said for the catalyst, right? If you add a catalyst, remember that will have more successful collisions, but that will mean more successful collisions in both directions. In both directions, both forward and reverse. So as a result, there is no change to the system, since just both the forward and reverse reaction speed up at the same rate. So no change to the system, and we would say no shift. In this exercise here, we're going to induce several shifts or several changes to the system, and looking at the system in question here, we can predict how the equilibrium system will react, how it will shift, and what side is favored. So here is a homogeneous system example. You have methane gas reacting with hydrogen sulfide gas, and the heat term is on the reactant side. So we know that this is an endothermic reaction. So because this is an endothermic reaction, the heat term goes on the reactant side because the reactants absorb heat to form products. The products here is carbon disulfide as a gas and hydrogen as a gas. The first change that's being imposed here is we are cooling the system. So by cooling the system, what we are doing there is we are removing heat. Okay, so we're removing heat from the system. Now, don't copy this, but what I would like to show you is one way of visualizing this. So, if you remove heat from the system or you decrease the heat in the system, recall that the system will respond to reverse your change. So if you remove the heat, the system will respond, so we'll shift left to produce heat, because the reaction as you go from from right to left will produce more heat, right? So if you take out heat here, the system will shift left to reproduce the heat that was lost. I'm going to just erase that. So as we can see here, the system will shift left and the change favors the reactants. All right. So if you remove heat then what ends up happening is the system will shift left to reproduce the heat that was removed. Now, you may be asking yourself a question: how does the system know to shift left or right? Well, it doesn't. It doesn't have sentience, or it doesn't have the ability to acknowledge that heat has been removed. However, remember that you have a forward reaction and a reverse reaction. What ends up happening here is that when you remove heat, heat is necessary for the forward reaction to happen. So when you remove that heat, that forward reaction rate temporarily slows down, and the reverse reaction in comparison to this forward reaction is now much faster. Those rates are unequal. Right? Because you've removed heat, this reaction, the forward reaction, slows down, and so the reverse reaction relative to the forward reaction now seems quite a lot faster. So the reverse reaction will quote unquote speed up to reproduce the heat. It doesn't actually speed up, but relative to the to the reaction that has been slowed down, it looks like it has. If you add CH4, okay, and again, I'm just going to draw this in so you can see this. If you add CH4 concentration, so increase this concentration, the system will shift to reduce that concentration. So the system shifts right to use up the excess CH4 that was added, right? Again, if we think about it in terms of rates, right? The forward reaction speeds up because you've increased the concentration relative to the reverse reaction. So it looks like the forward reaction is going much faster in comparison to the reverse reaction. Remember, at equilibrium, these rates are supposed to be equal. So by increasing the concentration of one, we throw them out of equilibrium temporarily and speed up the reaction in one direction. So if we added CH4 to the system, our system would shift right, and the change would favor the products. So the system will shift to consume the excess CH4 added. If you increase the volume, well, let's think about what change this has on the concentrations. So if we increase the volume, by increasing the volume, that will drop all the concentrations. All concentrations will decrease since the denominator goes up. And by increasing the volume, you are going to decrease pressure. So we take a look up at our system here, and if I decrease the pressure, well, the system will shift to the side with more particles to increase the pressure again. Because the more particles there are, the higher the pressure. So if we decrease the pressure, the system should shift right because there are 5 moles on the right side versus 3 moles on the left side. So the system will shift right. So we will have a shift to favor the products. So the system shifts to produce more moles of gas particles to restore pressure. Now, if you increase pressure by the addition of neon gas, remember, that's an inert gas, right? So I'll just put right there, that's an inert gas. There is going to be no shift, right? And the change will favor neither reactants nor products. So line through there, right? And so basically an inert gas will cause more collisions. However, no side is favored. So this will have no effect on the equilibrium system, especially since it is a gas system. If you add a catalyst, again, as we saw in the previous page, this will have no effect, right? And that's because both sides, both rates of reaction increase but remain equal. So that just means that you're speeding up the rate of reaction in both directions. Now, if you removed H2 gas, and so I'll go back up here, okay? If you take out H2 gas, well, the system is going to shift right to produce more H2 gas, because producing more H2 gas reverses the change that was imposed, right? If we remove H2 gas, then the reverse reaction slows down and the forward reaction relative to the reverse reaction seems to speed up. So if you remove H2 gas, the system will shift right to favor the products. So the system will shift to replace the products that was removed, or H2 that were removed. Okay, so hopefully you get the sense of how the system will shift in response to the change or stress imposed on the system. And this is Le Chatelier's principle. We can now do concentration versus time graphs. So on the right side, we have concentration, right? And this is going to be a qualitative graph. So these are concentrations. And this is time, concentration versus time. And in each of the these dotted lines are relative to all the various changes that, or stresses that were imposed in the previous example. So what I'm going to do is I'm going to create colored lines to represent the different reactants in each of these in the system. Okay, so what I'll do is I'll use green to represent CH4. Okay, and I'm just going to draw a straight line here. And so ideally you would be using a ruler. So we use a ruler to do concentration of CH4. Okay, and I'll use then I'll use a okay, let's just say I use an orange for H2S gas. This represents H2S gas. And then I'm going to use a different color for carbon disulfide. I'll use, I'll use blue for carbon disulfide. And I'll use purple for H2 gas. Okay, if we look at the stress that was imposed at A, the stress imposed at A was to cool the system, and so the system shifted left. So if the system shifted left, that means these were increased, right? The system shifted to replace the heat that was lost, and so concentrations of H2S and concentrations of CH4 will increase if the system shifts to the left. So I then draw the concentration of CH4 increasing and then stabilizing over time. And H2S will increase and stabilize over time. We'll go back to a constant concentration. And because the system shifted left, that means that the products were used to make that shift, and so then they decrease in concentration. Okay. If we look at B had a system that was, the system was shifting to the right because we added CH4. Now, if you add a substance, well, what that means there is that the concentration is going to spike up, okay? So the concentration will spike up. A spike up in concentration. So if I go down to CH4 over here, what will happen is the CH4 concentration will spike up because I added CH4, but then the system shifts to use that up, and it goes and it stabilizes. H2S will decrease because it gets reacted alongside the CH4. CS2, on the other hand, will increase in concentration because as CH4 and H2S react, carbon disulfide increases in concentration, and H2S will also increase in concentration and flatten out, okay? By the time they get to these dotted lines, they really should be straight lines. So using a ruler is quite paramount here. If you increase in volume, as I showed over here, I indicated that all the concentrations will drop because an increase in volume causes a decrease in concentration by the C is equal to N over V equation. So I have to now show all the concentrations spiking down because all the concentrations decreased. So that concentration decreased, this concentration decreased, and you get the picture. So they all go down. But it says that the system will shift to the right to favor the products. So it all decreases, but then the products will increase again because remember the system will shift to produce more moles of gas to restore the pressure that decreased. The reactants, however, will decrease in concentration because they're getting used up to form the products. Now, in both D and E, there was no shift. So this is fairly easy to represent on the graph. If there's no shift, then there's no change. It's just a straight line. Okay, same over here. Once we get to F, we see that the system shifts to the right to favor the products. If the system is shifting right in F to favor the products to restore the H that was removed, then that means that the reactants will decrease in concentration. So both methane and hydrogen sulfide will decrease in concentration because, there we go. It will decrease in concentration so that more H2 can be formed. And carbon disulfide will increase in concentration because products are favored. Now with H2, let's make a little note to ourselves. If we remove H2, then that will be a spike down because we are removing H2. So we decrease in concentration initially, and then the system restores that concentration. The last thing that we have to do is we have to indicate the stoichiometric coefficients, because all of these, this is the rough shape of the graph, but all of these are subject to stoichiometric multipliers, right? So CH4 has a stoichiometric coefficient of 1. Hydrogen sulfide has a stoichiometric coefficient of 2. Carbon disulfide is 1, whereas hydrogen is times 4. And we only need to do that once. Okay, just to indicate that these are the multipliers as a result of stoichiometry. So this was a homogeneous system in which all components were in the same gaseous or solution phase. You can, however, have a heterogeneous system, right? Which is where you have a solid in a solution system or gaseous system. Now, when you have a solid in the system, this changes the way we do our concentration versus time graphs. And so what I'll do is, if we have a graph here, so I'll draw a graph, and I'll color code each of these. So I'm going to make this one purple, okay, and NH3 will be green, and HCl will make that orange, okay. So I'll have orange and green and purple. If you add more pure solid, should the solid concentration spike up of it, and because it is a pure substance, it is a pure liquid or solid. Well, the concentration of a pure liquid or solid, right, if we think about that, concentration is given as moles over volume. Moles can be converted to mass using molar mass, so concentration is actually just mass over volume, which is concentration is density. So even though you add more pure liquid or solid, what will happen is it will not spike up even if you're adding more pure, for example, NH4Cl, because density stays constant. No spike when a solid or liquid added, since density, which is concentration, does not change. Remember that at a specific temperature, density for solids and liquids is constant. So this is a very important fact, and that's why we include it in the note package, which is, can the concentration of a pure solid or liquid be altered by adding more in a heterogeneous system? And we say no. There is no change in the concentration even if we add more to it, because there's no spike since the density does not change. Will adding more pure solid or liquid to a heterogeneous system cause a system to shift? And the question is, what is the exception? Well, if you add more solid, right, as we can see here, there will be no shift. Okay, when you add more pure solid or more pure liquid, there will be no shift, since the system is already at equilibrium. The exception to this is adding pure water to an aqueous system, as this will cause all your concentrations to decrease, right? Because that causes dilution. So that's the only exception where adding a pure substance can cause a system to shift, is adding water to an aqueous system, which causes dilution and then causes all the concentrations to decrease. Otherwise, adding a pure solid or liquid to a heterogeneous system will cause no shift. Homework questions are included on the next page with instructions indicated right here on how to complete them. Thanks for watching.